Alright, so today what we're going to do is we're going to talk a little bit about Chapter 9, which is all about nuclear chemistry. Now, nuclear chemistry is fairly different from all the chemistry that we've talked about before, and that's because we're dealing with the nucleus of the atom. So most chemical reactions that we've talked about in the past involve reactions or involve changes in the electrons around the atom. But here we're talking about reactions inside the nucleus. Okay, this is significant because this means that we're looking at reactions that could potentially, and normally do, change the identity of an element. Okay, something that we call transmutation. Okay, so you may have heard stories of people in medieval times trying to convert lead into gold. This is the type of thing that we're talking about here, except there are at least no common reactions that'll cause lead to turn into gold. Now, in addition to this possibility of transmutation, reactions inside the nucleus involve the breaking of interactions between nuclear particles. Okay, and this usually leads to the release of large amounts of energy. Okay, and we're going to kind of take that energy and we're going to kind of put it under the umbrella of being called radiation. Although radiation is actually pretty complex in and of itself. In fact, there are different types of radiation. And they differ in the way that they interact with matter and the way that they interact with magnetic and electrical fields. Okay, so you can imagine if somebody were to take a box that has a small opening and put some radioactive material inside of it, and then allow the radiation to be emitted, that they could put a photographic plate on the other side of it. When I say photographic plate, I'm talking about a lot like what they see, or what you see with X-rays and things like that. Basically, by being exposed to radiation, these photographic plates are going to change color. And what we find is that in the absence of any kind of an outside interference, the radiation that comes from that material is going to be focused in on one spot on that plate. Now, let's say we were to modify this setup a little bit. So we put a plate above and below that beam of radiation. Okay, we're going to put a positive charge on one plate and a negative charge on the other plate. And something very interesting happens when we turn this on. You see, what we wind up with is, instead of just getting one spot in the middle, we wind up with three spots. Okay, and what winds up being the case here is that when we have the plates energized, some of the radiation is being pulled closer to the positively charged plate. So basically its trajectory is being bent. Okay, and then some material is being bent in the opposite direction. Okay, so if you think about this, the stuff that's being pulled closer to the negative charge must itself be positively charged. Okay, the stuff that is pulled closer to the positive charge must itself be negatively charged. And then the stuff that's kind of staying in the middle there is not being affected by the charges, so it must not have any charge at all. Okay, the stuff that's positively charged we call alpha radiation, Okay, that's the Greek letter alpha. The stuff that was negatively charged is called beta radiation, and the stuff that has no charge at all is called gamma radiation. Now, these names sound pretty fancy, but when you think about it, alpha, beta, and gamma are all just the first three letters of the Greek alphabet, so it's just like they called them A, B, and C, so nothing too fancy. Okay, now, it turns out that what these three different types of radiation actually are, well, in terms of the positively charged alpha particles, these are actually helium atoms. Okay, actually I should say helium nuclei. Okay, so there's no electrons on there, and if you remember the system that we taught earlier in the semester, we can figure out the mass and the atomic numbers here, and we see that helium is going to have 2 protons and a mass number of 4, which means it has 2 neutrons. Okay, the gamma radiation, it turns out, is just high energy light. Super high energy. Like so high energy that it will cause severe tissue damage if you got exposed to it. Okay, and then the beta radiation is actually high energy electrons. Now, that by itself should be a little bit troubling for us because we said that these are nuclear reactions taking place inside the nucleus, and here we have somehow electrons being emitted. Now that's, again, very bizarre, and we'll talk more about that as we move into the next video.